In this video, we are going to look at how to use the experimental data to determine the order of a reaction with respect to each of the reactant using initial rate method. Hey, I'm Teacher Tan. If you like my video, do remember to click on the subscribe button below so that you won't miss any notification as I update my channel.
Order of a reaction must be determined experimentally. If given experimental data, we can use initial rate method to determine the order of a reaction with respect to each of the reactant. Or if given experimental data, we can also plot different graphs to determine the order of reactions with respect to that particular reactant. For example, we can plot reactions rate versus concentrations of reactant graph, and from the Red law or Red equations, we know that different order of reaction has different shape of rate versus concentrations graph. Therefore, from the shape of the graph, we can determine the order of the reaction with respect to that particular reactant. Or we can also plot concentrations versus time graph and determine the half-life, and from the half-life, we can determine what order of the reactions with respect to that particular reactant. Or we can use linear graph method by plotting different integrated Red law graphs to determine which one giving the linear shape graph to determine the order of the reaction with respect to that particular reactant. Now we move on to look at initial rate method. Example 1 only involves one reactant, which is compound A. We are going to look at how we can use the experimental data to determine the order of reaction in compound A, and then from there we can write the Red law or Red equation and calculate the rate constant and determine the initial rate when the concentrations of reactant A is 0.4 molar. In the part A of the question, we want to write the Red law or Red equation. To write Red law or Red equation, we must know the order of reaction with respect to the reactant. But in this question, we do not know the order of reactions with respect to the reactant A. So what we can do is, we write the Red law in general form first. We can write the Red law as rate equals to rate constant multiply with the concentrations of reactant A raised to the power of x. And the x here is the order of reaction with respect to reactant A. To find the order of reactions with respect to reactant A, the x, we can divide the rate of one experimental data with the rate of another experimental data. In this question, we are being given two sets of experimental data. So one, I will call it as experiment 1 data, and another one is experiment 2 data. So usually when want to divide the rate of one experimental data with the rate of another experimental data, I will use the larger rate value to divide with smaller rate value. In this question, experiment 2 has larger rate value, so I will use experiment 2 rate data to divide with experiment 1 data, which has smaller value. So experiment 2 rate data divide with experiment 1 data. When we divide the rates, we need to divide the rate constant and the concentrations term as well, because remember in Red law, the rate is equal to rate constant multiplied with concentrations of reactant A raised to the power of x. So when we divide the rate, we also need to divide the rate constant and the concentrations terms. When we do the divisions for rate constant and concentrations term, we need to substitute the concentrations value for each experiment into the term. Like for example, in experiment 2, the concentrations of A is 0.3. So we can substitute 0.3 concentrations of A into the concentrations term. That is corresponding to the rate for experiment 2. And do the same thing for experiment 1. The concentrations of A is 0.2, so we can substitute the concentration A 0.2 corresponding to the reactions rate for experiment 1 into the expressions. Then we can cancel out the rate constant, and then mathematically we can simplify 0.3 raised to the power of x divide with 0.2 raised to the power of x to 3/2 raised to the power of x. And 1.5 divided by 0.68, we can simplify to 38 divided by 17. Then to find x, basically we just need to apply logarithm. So we log the term on the left and also log the term on the right to find the x value. And the x value is determined to be 2. And this 2 basically means that this reaction is second order with respect to reactant A. Now we know the order of reaction with respect to reactant A, then we can write the red law or red equation by substituting the x into the red law or red equation. So for this question, the red equation or red law then can be written as rate equals to rate constant multiplied by concentrations of A raised to the power of 2. In the part B of the question, we want to find the rate constant K. In part A, we already have our rate law. So to find rate constant, we just need to rewrite the whole rate law or rate equation in terms of rate constant. So that will be the rate constant K equal to reactions rate divided by the concentrations of reactant raised to the power of 2. Then we can choose either experiment 1 data or experiment 2 data into the rate constant expression to find the rate constant value. So for example, in this question, I'm choosing the data from experiment 1. So I substitute the rate for experiment 1 into the rate constant expression and also the concentrations of A data from experiment 1 into the rate constant expression to give the rate constant equal to 17. And how do we determine the unit for rate constant? So for rate, the unit is mole per dm cube per minute. And for concentrations of A is mole per dm cube. And here is second order raised to the power of 2. So means that the overall unit will be mole squared dm minus 6. And then we can cancel 1 mole. So we have per mole remain. And for dm per dm cube, can also cancel with the dm to the power of negative 6 to give us dm cube, and per minute still remain to give us the unit for rate constant as per mole dm cube per minute. Then in the part C, so now the concentrations of reactant A given is 0.4 molar and asks us to determine what is the rate or initial rate of the reaction. To determine this, we just need to substitute the rate constant that we find in part B and also the concentrations of reactant A given into the rate law equation that we get in part A to find the initial rate when the concentrations of reactant is 0.4 molar. So when the concentrations of reactant A is 0.4 molar, it is determined that the initial rate is equal to 2.72 mole per dm cube per minute. In example 2, the initial rate is measured in terms of disappearance of oxalic ion with several concentrations of mercury 2 chloride and oxalic ion. In part A, we need to determine the rate law or rate equations for the reaction. To determine the rate law, first we need to determine the order of reactions with respect to each of the reactant. From the rate law, then we can use one of the experimental data to calculate the rate constant, and then we can calculate the rate of appearance of carbon dioxide from the concentrations of reactants, mercury 2 chloride and oxalic ion given in part C. To determine the rate law or rate equation, first we can write the general form of rate law or rate equations for these reactions first. We can write it as rate equals to rate constant K multiplied by concentrations of mercury 2 chloride raised to the power of X. The X here, because we do not know the order in mercury 2 chloride yet, so we'll assume it's X. multiply with concentrations of oxalate ion raised to the power of y. Again, we do not know the order with respect to oxalate ion, therefore we'll assume it's y first. Then, to find the order with respect to mercury 2 chloride, X, we need to make sure that the concentrations of another reactant, oxalate ion, remains constant. From the experimental data given, we can see that is the data of experiment 1 and experiment 3 having the concentrations of oxalate ion given are constant. Therefore, to calculate X, the order for mercury 2 chloride, we can use the data from experiment 1 and experiment 3. So the initial rate for experiment 1 is larger than experiment 3. Therefore, to calculate X, we can use the rate for experiment 1 divided by initial rate of experiment 3, which is equal to 1.65 times 10 to the power of negative 5 divided by 4.13 times 10 to the power of negative 6. When we divide the reactions rate, we also need to divide the whole rate constant and the concentrations term for each of the experimental data. For experiment 1, the concentrations for mercury 2 chloride is 0.132, so we substitute that into the equations, and the concentrations for oxalate ion is 0.12, so substitute that into the equation. And for experiment 3, the concentrations of mercury 2 chloride is 0.033, so substitute that into the equation, and the concentrations of oxalate ion is 0.12, so substitute that into the equation. Then for the rate constant K, we can cancel out, and for 0.12 to the power of y, we can cancel out, and then 1.65 times 10 to the power of negative 5 divided by 4.13 times 10 to the power of negative 5 will give us 3.995, while 0.132 can divide by 0.033 to the power of x to give us 4 to the power of x. And then to find x, we can log both sides. So when we log both sides, we can determine the x as equal to 1. Therefore, it means that the reaction is first order with respect to mercury 2 chloride. Calculate y, we need to measure that the concentrations of another reactant, which is mercury 2 chloride, remains constant. And from the experimental data, we can see that is experiment 1 and experiment 2 having the concentrations of mercury 2 chloride remains constant. Therefore, to find y, we need to use the experimental data from experiment 1 and experiment 2. To find y, we need to use the rate of reactions 2, which is 2.64 times 10 to the power of negative 4, divided by initial rate of experiment 1, 1.65 times 10 to the power of negative 5. And when we divide the reactions rate, we also need to divide their rate constant and also the concentrations of reactant respectively. For experiment 2, the concentrations for mercury 2 chloride is 0.132, while the concentrations of oxalate ion is 0.480. So substitute them into the equation. And for experiment 1, the concentrations of mercury 2 chloride is 0.132, while the concentrations of oxalate ion is 0.12 molar. Substitute that into the equation. Then, for the rate constant, we can cancel out, and the concentrations of mercury 2 chloride 0.132 to the power of x can cancel out. And then the rate for reactions in experiment 2 divided by the rate for experiment 1 to give us 16, and 0.48 divided by 0.12 to give us 4 to the power of y. And then we can find that the y is equal to 2, and therefore the reaction is second order with respect to oxalate ion. So after we have found what is our x and y, then we can write the rate law or rate equation as rate equals to rate constant multiplied by concentrations of mercury 2 chloride raised to the power of 1, because x is equals to 1 and the reaction is first order with respect to mercury 2 chloride, and multiply with concentration of oxalate ion raised to the power of 2, because y is equal to 2 and the reaction is second order with respect to oxalate ion. In part B, we need to find the rate constant. How to find the rate constant? We just need to rewrite the rate law equation that we have found in part A in rate constant term. So that will give us rate constant K equals to rate divided by concentrations of mercury 2 chloride multiplied with concentrations of oxalate ion raised to the power of 2. we can choose one experimental data. Like for example here, I choose experiment 1 data and then substitute that into the rate constant term to get the rate constant as 8.681 times 10 to the power of negative 3, the unit for the rate constant. So basically, molar we can cancel out. So what remains is per molar square and per second as the unit for the rate constant K. Question part C asks what is the rate of appearance of carbon dioxide when the concentrations of mercury 2 chloride is 0.1 molar and the concentrations of oxalate ion is 0.25 molar. For these questions, we must know that the initial rate here is referring to the rate for the disappearance of oxalate ion. Therefore, the rate determined in rate law or rate equation is referred to the rate of disappearance of oxalate ion. To determine the rate of appearance of carbon dioxide, first we need to determine what is the rate of disappearance of oxalate ion when mercury chloride concentrations is 0.1 molar and the concentrations of oxalate ion is 0.25 molar. To determine the rate of disappearance of oxalate ion for these two concentrations of mercury chloride and oxalate ion, we just need to substitute them into the rate law or rate equations that we have found in the part A. And for the rate constant, we can substitute the rate constant value that we have determined in the part B. And we must know that the rate in the rate law or the rate equations here is referred to the rate of disappearance of oxalate ion. And therefore, the rate of disappearance of oxalate ion is determined to be 5.425 times 10 to the power of negative 5 molar per second. To determine the rate of disappearance of oxalate ion, then we can determine what is the rate of appearance of carbon dioxide. Step number 1 is based on the stoichiometric coefficients in the balanced chemical equations. We write the differential rate equation for the reaction. Then, step number 2, we write out what is being given and what we want to find in rate of appearance and rate of disappearance form. Like for example, in this question, in part B, we have found that the rate of disappearance of oxalate ion equals to 5.425 times 10 to the power of negative 5 molar per second. So in step number 2, we need to write this in the rate of disappearance of oxalate ion form. And we are looking for rate of appearance of carbon dioxide. So write it in the rate of appearance of carbon dioxide form. Then in step number 3, for each of these terms that we have written in step number 2, we write them in terms of their equivalence based on the chemical equation. Like for example, for the rate of disappearance of oxalate ion, based on the stoichiometric coefficients in the balanced chemical equation, it is equivalent to 1 mole. And for the carbon dioxide, rate of appearance of carbon dioxide, the stoichiometric coefficients in the balanced chemical equations is 2. Therefore, we can equate the rate of appearance of carbon dioxide equivalent to 2 mole. Then, to find the rate of appearance of carbon dioxide, we can do cross multiplying. And therefore, the rate of appearance of carbon dioxide is equal to 2 multiplied by the rate of disappearance of oxalate ion. And for the rate of disappearance of oxalate ion, we know that it is equal to 5.425 times 10 to the power of negative 5 molar per second. We just need to substitute the value into the term to give us the rate of appearance of carbon dioxide is equal to 1.085 times 10 to the power of negative 4 molar per second. Then we just need to conclude our calculations by writing the rate of appearance of carbon dioxide equals to 1.085 times 10 to the power of negative 4 molar per second.